Alright, hello everybody. This video is going over the 1.5 multiple choice and FRQs in the Unit 1 booklet. Number 1 says the atom that contains only one electron in the highest occupied energy sublevel is, and then we have 5 choices. So when it's saying the highest occupied energy sublevel, that means we're going to look at its electron configuration for each one. So first up, let's look at sulfur. If we start our electron configuration at the noble gas neon, our electron configuration would be 3s2 and then 3p4. And that is because it is the fourth electron in the p sublevel. So since it has 4 electrons in the highest energy sublevel, that is not our answer. So next up, we're going to do calcium. So if we start at our noble gas electron configuration, that would be argon, and then the electron configuration would be 4s2. So since it has 2 electrons in the highest occupied energy sublevel, this would also not be our answer. Next up, we're going to do gallium. Now already you can see that gallium is the first element in the p sublevel, so you know this is going to be our answer, but we're going to continue doing electron configuration just to make sure. So if we are doing the electron configuration of gallium, we would start again at argon. It would be 4s2, 3d10, and 4p1. Since it only has 1 electron in the highest occupied energy sublevel, which is 4p, then that would be our answer. Alright, number 2 says the atom that contains exactly 2 unpaired electrons is which of the following? We are given 5 answers here. We're going to start from the bottom, bromine. Bromine is in group 17, which means it has 7 valence electrons. So when we draw out the Lewis dot structure of bromine, we'll have 7 valence electrons. That means it only has 1 unpaired electron, so bromine would not be the answer. Next up, we have antimony. Antimony is in group 15, which means it has 5 valence electrons. 1, 2, 3, 4, 5. That's going to have 3 unpaired electrons, so that would also not be our answer. Next up, we have gallium. Gallium is in group 13, which means it has 3 valence electrons. 1, 2, 3. So that has 3 unpaired electrons, so that would also not be our answer. Next up, we have calcium. Now, calcium is in group 2, which means it has 2 valence electrons. So its Lewis dot structure is like this. However, since we're in the s sublevel, if we write out the electron configuration with the arrow diagrams, in s, so this would be 4s, these 2 electrons are in the same orbital, which means they are paired technically. So calcium would not be the answer for this question, and it'll make sense when you see sulfurs. Now sulfur is in group 16, which means it has 6 valence electrons, 1, 2, 3, 4, 5, 6, which means it has 2 lone pairs and 2 unpaired electrons. So A would be your best answer for this question. Alright, number 3 says, which of the following ground state electron configurations represents the atom that has the lowest first ionization energy? So remember, ionization energy increases as you go up and to the right on the periodic table. So let's first identify all of these elements on the periodic table. So A is 1s2, 2s1. Remember, this is 1s and it's full because it has 2 in it. And this would be 2s, and since it's the first one, this one would be lithium. Next up is 1s2, 2s2, 2p2. So since it's ending in 2p2, we know it's going to be in the second period in the p sublevel. and it will be the second one. So this would be carbon. Then we have 1s2, 2s2, 2p6. Again, it will be in the second period and the p sublevel, and it will be the sixth element. So this one would be neon. Then we have 1s2, 2s2, 2p6, 3s1, which means it will be ending in the third period in the s sublevel, which is this sublevel, in the first electron. So this would be sodium. So now that we have our 4 elements on the periodic table, we can look at the first ionization energy trend, and since it's asking for the lowest first ionization energy, according to the trend, that would be sodium, which would be D. Alright, number 4 says, which of the following is the ground state electron configuration of the F- ion? Remember, when it has a negative charge, that means you have 1 extra electron than the element itself. So let's find fluorine on the periodic table, and let's write out its electron configuration before it becomes an ion. So it would be 1s2, 2s2, 2p5. Remember these exponents, the 2, and the 5, those are going to be the amount of electrons in each orbital. So right now we have a total of 9 electrons. Now, a F- ion is saying that it has 1 extra electron, so it's going to have a total of 10 electrons now. So instead of 1s2, 2s2, 2p5, its new electron configuration would be 1s2, 2s2, 2p6. Number 5 says, which of the following best represents the ground state electron configuration for an atom of selenium? So let's find selenium on the periodic table. So selenium is in the p sublevel. It's in the 4th period, so we know it's going to be ending in 4p, and it is the 4th element in that sublevel. So we know it's going to be ending in 4p4. So I always like to start there in case I can cancel out the rest of the options, and in this case I can. The only one ending in 4p4 would be C. So I just want to double check that this is correct. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then comes 3d10, and then 4p4. So that is the correct electron configuration for selenium. How many protons, neutrons, and electrons are in a 56 iron atom? So remember, 56, or the number on the top, is the mass number, so that's the number of protons and neutrons. And 26 is the atomic number, which means 26 is the number of protons. So in order to get our number of neutrons, we're going to take 56 and subtract 26, so that's going to give us 30 neutrons. And since there is no charge on this atom, then we know that the electrons are going to equal the protons. So this means we would have 26 protons, 30 neutrons, and 26 electrons. So your answer would be A. Of the following electron configurations of neutral atoms, which represents an atom in an excited state? All of these answer choices here are in neutral states. I actually made a mistake when writing out this electron configuration for B. B should say 1s2, 2s2, 2p5, 3s2. So remember, an excited state is when an electron temporarily occupies an energy state greater than its ground state. And what that's going to look like in electron configuration is a previous sublevel not completely full. So if we look at A, we have 1s2, which is full, and 2s2, which is full, so that would not be the answer. If we look at C, 1s2 is full, 2s2 is full, 2p6 is full, so that would not be the answer. D, 2s2 and 1s2 are full, 2p6 and 3s2, those are all full before moving on to the highest energy sublevel. And then E, we have 1s2, 2s2, 2p6, 3s2, those are all full as well. So the answer would be B if it was written out correctly, which 2p was supposed to have the number 5 as the exponent. which means the electron that was supposed to be in 2p5 is in the excited state and was moved into 3s. So if you could just change this number 6 on your booklet, that would be great, and B is the answer. All right, number 8 says the effective nuclear charge experienced by the outermost electron of sodium is different than the effective nuclear charge experienced by the outermost electron of neon. This difference best accounts for which of the following. So first, let's go into effective nuclear charge, which is written out as ZeFF. Now we're going to start with the effective nuclear charge of sodium, and the way that you calculate this is you take the total nuclear charge, or the total number of electrons. In this case, sodium has 11. And you're going to subtract the electrons in the previous energy level. So in the first energy level, we have 2 electrons, and in the second energy level, we have 8 electrons. So that's going to give us an effective nuclear charge of 1 for sodium. Then, if we do the same thing for neon, neon has 10 electrons, and if we take away our 2 energy levels, that's going to leave us with an effective nuclear charge of 0. Now, this is really showing you the first ionization energy of these 2 elements, because if you notice, sodium has 1 extra electron in the outermost energy level, which means it's much easier to remove than neon's outermost electrons, which are in a full octet in the second energy level. So because of that, the answer for this one would be B. Which of the following is the electron configuration of an excited atom that is likely to emit a quantum of energy? So this part in the end here is kind of irrelevant. I mean, when you have an excited atom, it is likely to emit a quantum of energy. So that's not really necessary to get hung up on. What you're really looking for is an electron configuration of an excited atom, which we've already done. Now, there is another mistake with these. I must have just been typing too fast when doing the electron configurations. So in E, this is supposed to say 3s1 here. So what we are looking for is a previous sublevel that is not filled. And since I just kind of showed you that, E would be your answer, because 3s should say 3s2, but it's 1. So the electron that was supposed to be in 3s now jumped up into 3p. So E would be your answer here. Which of the following represents a pair of isotopes? Now remember, isotopes are going to be of the same element, which means they're going to have the same atomic number. So when we're looking at all these answer choices, you need to find the pair of atoms that have the same atomic number. In this case, the only option here would be D, where we have the atomic number of 7, which means both of these would be a nitrogen isotope. So D would be your answer. All right, which of the following represents the ground state electron configuration for the manganese 3+ ion? So manganese is in group 7 here, and we know that the standard electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d, 1, 2, 3, 4, 5. Now, this positive 3 means that it has 3 more protons than electrons, but what that really means is that it lost 3 electrons. So when we are taking away those 3 electrons from our electron configuration, remember it has to be the outermost first. So since we have 2 electrons in the outermost sublevel of 4s, that means those 2 have to be taken away first, and then we would take away 1 from 3D. So our new electron configuration would end up being 1s2, 2s2, 2p6, 3s2, 3p6, 3d4. Which of the following shows the correct number of protons, neutrons, and electrons in a neutral cesium-134 atom? So remember, this 134 is the mass number, which means it's the number of protons plus the number of neutrons. And cesium has an atomic number of 55, which means it has 55 protons. And if it's a neutral atom, which in this case it is, it also has 55 electrons. So right off the bat, we can cancel out C, we can cancel out D, and we can cancel out E. And now we have to find out the number of neutrons. So in order to find that out, we're going to take 134 and subtract 55, and that's going to give us 79 neutrons, so the answer would be B. All right, use the principles of atomic structure and or chemical bonding to explain each of the following. In each part, your answers must include references to both substances. So A says the atomic radius of lithium is larger than that of beryllium. So if we look at lithium and beryllium, they are in 2s of the periodic table. We know that the atomic radius of lithium is larger because of the atomic radius trend. And the atomic radius trend is the way that it is because as you go right on a period on the periodic table, you are increasing the number of protons, which is going to pull those electrons closer to the nucleus. So one of the answers for A would be that beryllium has more protons than lithium. B says the second ionization energy of K is greater than the second ionization energy of Ca. So let's look at the second ionization energy of each of these. So the first ionization energy of K would be its 1 valence electron. So if that got taken away, it would then go to its previous sublevel, which is then going to be a full octet. Then if we go to calcium, its first ionization energy would be taking away one of these 2 valence electrons, and its second ionization energy would be taking away the 1 valence electron. Now the reason that the second ionization energy of K is greater is because now K has a full octet of electrons, which means the ionization energy, or the energy it's going to take to remove one of those electrons, is going to be much larger than that of the single electron in the calcium. C says the carbon-to-carbon energy in C2H4 is greater than it is in C2H6. Now let's draw out these Lewis structures. So we have C2H4, which means the bond energy between these 2 carbons would be a double bond. And for C2H6, you have a single bond between your carbons and a single bond to all of the hydrogens, which means that the bond energy is greater in C2H4 because you have a double bond between the 2 carbons. And then D says the boiling point of Cl2 is lower than the boiling point of Br2. So since chlorine has less electrons than bromine, there will be less energy required to overcome the forces between the chlorine molecules than the forces between the bromine molecules. And then number 2, answer the following questions related to sulfur and one of its compounds. A says consider the 2 chemical species, sulfur and the sulfur -2 ion. Write the electron configuration of each species. So the electron configuration for sulfur, which is in group 16 of the periodic table, would be 1s2, 2s2, 2p6, 3s2, 3p4. Now, S with a -2 charge means it has 2 extra electrons. So we can just add 2 electrons into the 3p sublevel, and our electron configuration for S2- would be 1s2, 2s2, 2p6, 3s2, and 3p6. Now I did want to note if you wrote this in noble gas electron configuration, that would also be counted correct. AI2 says explain why the radius of S2- ion is larger than the radius of the S atom. So it's important to note that the reason that the S2 minus ion is larger is because you are adding electrons without adding protons. So if you have an S atom that has 4 valence electrons, or I'm sorry, 6 valence electrons, if you are adding 2 more, you are just adding more electrons to the outermost valence shell. So you're not adding more protons to bring them in closer to each other or to increase the attraction. So by adding more electrons without adding more protons, you are just increasing the radius. It can also be written that those 8 valence electrons in the S2 minus ion have a higher repulsion of the electrons, which is going to increase the radius of that ion. The next one says, which of the two species would be attracted into a magnetic field? Explain. So the regular sulfur atom would be attracted into the magnetic field because it does not have a full octet. So it is going to be searching for those 2 electrons, which means it's going to be more likely to be attracted to the magnetic field. Whereas the sulfur 2 minus ion has all paired electrons, so it is not going to be attracted to the magnetic field. So for B, it requires less energy to remove an electron from a sulfide ion than from an argon atom. And that's because a valence electron in the sulfide ion is less attracted to the nucleus because it has a charge of only positive 16 than is a valence electron in the argon atom because it has a charge of 18. So they may have the same number of electrons, but since sulfur has less protons attracting those electrons, then it's going to be easier to remove an electron from the sulfide ion.